All right, welcome. Today we are diving headfirst into the absolutely incredible world of computational chemistry. This is where scientists get to build, test, and really understand molecules without ever having to touch a single test tube. It's pretty wild.
So just imagine this for a second. You've got a million potential new drugs, but maybe only one of them is the big breakthrough you're looking for. How in the world do you test all of them? I mean, the time, the money, it would be absolutely astronomical.
Well, here's the trick. You don't do it in the real world. You do it on a computer. You build them, you twist them, you see how they react, all inside a simulation. And that is the incredible power of computational chemistry. So what exactly is this field, anyway? Honestly, the best way to think about it is like a digital microscope for the atomic world. It's a whole suite of tools that lets us predict what molecules are going to look like and how they're going to act.
Okay, so at its core, computational chemistry is all about using computer programs to solve chemical puzzles. See, every single molecule has this desire to be in its most stable, lowest energy state. These methods calculate the total energy for every possible 3D shape. We call those conformations, to find that one perfect stable form. And to get this done, chemists have two totally different ways of thinking about it.
Let's start with our first approach. It's a method called molecular mechanics, or just for short. Think of this as the fast, no-nonsense workhorse of the field. And it's built on a kind of physics that's probably going to feel pretty familiar.
You know, the beautiful thing about the model is its simplicity, and that's the key to its speed. It just pretends that atoms are simple little spheres, and the bonds connecting them are tiny springs. That's it. By totally ignoring the messy, complicated world of electrons, it can just use classical physics. We're talking Newton's laws here, to get the job done and get it done fast.
So the computer figures out the total energy by basically just adding everything up. How much energy does it take to stretch those bond springs? How much to bend the angles between them? And what about the little pushes and pulls between atoms that aren't even bonded to each other? You just add it all together, and bam, you get the total energy for that specific shape.
And this whole process is super practical. Say you want to build a molecule like paracetamol. A chemist can literally just grab the building blocks from a digital library, stitch them together on screen, and then just tell the computer, hey, go find the lowest energy shape. The program then tweaks all those little springs and spheres until it finally settles on the most stable 3D structure.
But, you know, the classical world has its limits. To get a really deep, fundamental understanding, we have to go somewhere else. We have to enter the quantum world. This is the other side of the coin from quantum mechanics, or QM. It is deep, it is super accurate, and yeah, it is way more demanding on our computers.
Now, the number one most crucial difference between these two boils down to one thing: electrons. Molecular mechanics, to get its speed, completely ignores them. But quantum mechanics, it is all about the electrons. It dives right into their weird, complex, wave-like behavior, which, by the way, governs literally everything about how molecules form bonds and react.
And right at the heart of QM is this famous beast, the Schrödinger equation. Now, don't worry about the math. Seriously, just think of it like a fundamental recipe. If you can solve this equation for a molecule, it will tell you basically everything you could ever want to know about its energy and its electrons. It's kind of like the ultimate source of truth in chemistry.
Now, actually solving that equation is incredibly difficult, so chemists have come up with different flavors of QM to get a really good approximation. You've got ab initio methods, which means from first principles, they use only pure theory. A really popular version of that is DFT. And then you have semi-empirical methods, which kind of cheat a little by plugging in some real-world experimental data to speed the whole process up.
And this brings us to the central dilemma, the great trade-off that every computational chemist faces every single day. You've got the fast, classical world of on one hand, and the super accurate quantum world of QM on the other. You just can't have both at the same time. You always have to make a choice.
And boy, are the differences stark. QM can actually model a chemical reaction, the real breaking and forming of bonds, because it understands electrons. It just can't do that. But then when you look at size, the roles completely reverse. QM maxes out around a few hundred atoms. Can handle tens of thousands, or even more, like a giant protein. It's the classic trade-off. Do you need the incredible detail of QM, or do you need the massive scale of
And I mean, the difference in scale here is just massive. Look at this. The most hardcore ab initio methods can handle maybe 100 atoms. DFT pushes that up to 1,000, which is great. But we're talking 100,000 atoms or more.
There's even a kind of silly mnemonics to remember the order of increasing system size. All dogs smell more. For ab initio, DFT, semi-empirical, and molecular mechanics. It works.
So, you see, it's not really about which method is better. It's all about choosing the right tool for the specific job you need to do. Each one has its own purpose, and in that purpose, it absolutely shines.
You'd grab your molecular mechanics toolkit when you're dealing with huge molecules, like watching a protein wiggle and fold in real time. Or, think back to our first question, if you need to rapidly screen millions of potential drug candidates to just see which ones might fit into a target, is your only real option. It's built for scale, it's built for speed.
But the moment you need to understand an actual chemical reaction, I'm talking about how bonds snap apart and new ones form, you have to use quantum mechanics. There's no way around it. When you need to calculate really precise electronic properties or see what a high-energy transition state looks like, only QM has the accuracy to give you an answer you can trust. It's for when you need to be right. And, after all those intense calculations, all that abstract data doesn't just stay on a spreadsheet. No, it gets turned into these beautiful, tangible 3D images, like a space film model, which really shows you the volume each atom takes up.
Or maybe you prefer the classic ball and stick model, which gives you a really clear view of the molecule's skeleton and how it's all connected.
And for those gigantic biomolecules, we often use a ribbon model. It's perfect for tracing the complex twists and turns that give a protein its unique function.
And all of this really leads to one final powerful question. We have these incredible digital tools that let us design and test molecules with more and more accuracy and speed, everything from new medicines to brand new materials. So, if we can truly model reality inside of a computer, what's the limit? What will we build next?